Hello, dear students. Hope you are doing well. In today's lecture, we are going to continue our previous lecture about the rapidly varied flow. This is the second part of chapter 11, and in this part, we will see flow behavior before and around a sudden transition. We will consider a hump in front of flow, and we will evaluate the variation of water surface profile above the hump. Uh, Before going to the materials, I would like to show you some figures that displays what I mean by a hump or water surface variation above or before the hump. Actually, you see a piece of wood here. This is a flow, and we have a flow. This is flow direction, and hump is an obstacle in front of flow. As a result of such an obstacle, it is expected that some sudden change on the flow surface, as you see here, appear. Therefore, this would be a case of rapidly varied flow. But uh, this kind of change can vary with respect to the condition of flow at upstream. Here, I mean here, upstream of a hump, and also height of the hump is the other important parameter which dictates to the flow uh, uh, how it must change its regime before or after the hump. This is an example of a you see we might have a critical flow here, but here we have a rapidly varied flow with higher depths than here, and we see that when flow reaches to the hump, its surface goes down, and we have a drop on the water elevation at the location of a hump. However, this is not a single case or lone possible option. We have another possible way, and as you see here, we have a kind of flow which seems to be supercritical, and when the flow meets the hump, the elevation raises. This is the adverse condition than the previous. If you remember here, when flow reaches to the hump, we have drop in the elevation, but in this case we have a sudden rise in the elevation or in the depths of flow above the hump. And also this is another case that you see we have a relatively higher depths with respect to the previous examples, and also we have higher height for hump. Several piece of woods are located above each other, and we have a sudden raise just above the hump. You see, more or less we have a constant elevation, but just above the hump we have a sudden raise, and uh, the elevation of or depths of water here would be critical depths. You might know uh, that uh, to calculate elevation of uh, flow at this flow or before hump, after hump, we need to use energy equation, and the topic of energy equation already discussed in previous lecture. Therefore, considering these three different conditions, we will try to find some unknowns. For example, a kind of question can be for a given discharge here and for a given depth, what would be the depth of flow above the hump, or some other kind of questions that today I'm going to show you these kind of questions. Okay, this is a general formulation of the energy at open channels, and you know that we said between two cross section at upstream and downstream we will have such a uh, equality. Specific energy at section 1 plus the elevation of the bottom of the cross section at section 1 uh, is equal to the specific energy at second cross section plus um, elevation of the bottom of the second cross section from datum, and plus loss of the energy or head losses. And you remember that in previous lecture we said that for the case of uniform flow we can remove z terms. For the case of horizontal flows we can remove z terms, and for the case of the neglecting loss of the energy, and we can assume that E1 equals to E2, which would be the case of uniform flow. Therefore, in these examples that we are going to solve in today's lesson, we will use this equation or its simplified forms based on the information given in each example. Here we see the first example. Let's read the question together and to see which form of this general formula must be used. A steady uniform flow in a rectangular channel of width 5 meter is interrupted by the presence of a hump of 0.2 meter in the channel. The upstream depth is 1.25 meter and the discharge is 10 cubic meter per second. Find the depth of the flow at position 2, taking alpha equals to 1 and assume no energy loss. This is very informative question, and let's review the knowledge that we know from this question. The question says that upstream depth equals to 1.25, and also we know that we have a hump with the height of 0.2 meter. The discharge in this canal equals to 10 cubic meter per second. There is no energy losses, therefore we can remove this term. There is the information about alpha. Alpha, you remember, that is the kinetic energy correction factor. It can be assumed 1. Therefore, when we are going to calculate specific energy, we can neglect the coefficient factor, kinetic energy coefficient factor. And what is the expected in this question? We are going to determine the height of the flow above the hump. The figure says that, or figure indicates that we might have a decrease or we might have a drop when the flow meets the hump, but it is also possible in some cases we have a increasing depths, as we show we saw in previous slides. So let's go to the solution, but before going to solution, I would like to repeat that we must use the HL, and we see that this is a horizontally built canal, therefore there is no Z1. And what we can use this version of the previous formula, which says E1 equals to E2 plus delta Z. In fact, when we removed Z1 and HL, what is the remaining is E1 equals to E2 plus Z2. Z2 here is our delta Z, or elevation of the bottom of cross section at the second point. So to find this elevation, we have such a equation, and let's replace the relevant terms for specific energy. You remember that specific energy is a function of velocity and depth. Therefore, E1 equals to y1 plus v squared over 2g, and similarly E2 equals to y2 plus v squared v2 squared over 2g plus delta z. So what is the known and unknown parameters in this equation? Y1 is at hand from the question. V1 is unknown, but we have Q. Therefore, easily we can calculate this V based on the continuity equation. As you see here, delta Z is at hand, but Y2 and V2 is not at hand, and let's see how we can solve it. Okay, to calculate V1, we divide discharge by the area of this rectangular cross section, which equals to 5 times 1.25. Therefore, from here we can calculate velocity equals to 1.6 meter per second. Now I have velocity and y at upstream of the hump. How about the velocity at downstream of, or at the above the hump? I know that a multiplication of velocity here at the area here must give me a discharge, because discharge is constant along the channel. Therefore, I can find a relation for V in terms of Y. You see that V is 2 equals to Q over By. Therefore, Q is constant equals to 10, and V2 equals to 10 over 5Y2. And 5 is a constant bottom width, even in section 1 or section 2. Bottom width is constant. Therefore, V2 equals 2 over Y2. Now, in this equation, I have Y1 known, V1 known, Y, I don't know Y2, and I don't know V2, but I know that V2 is a function of V2. Therefore, I can write this equation like this: 1.25 plus 1.6 squared over 2g equals y2 plus 2 to the power of 2 divided by 2g y2 squared plus 0.2. So this equation must be solved for y2, and you see that this is a equation in terms of y, and if you do a little algebra, you can transform this equation to this form, and here you see that this is a function of y. This is a cubic equation with respect to the y. Therefore, by solving this equation, you will have 3 values for y2, and these are those possible values: y2 equals to minus 0.36, 0.59, and 0.96. This is mathematically true because each cubic equation will have 3 roots, but physically negative solution or negative root of this equation is not acceptable in hydraulics, because water depths cannot be negative. Therefore, the unknown y would be one of these two values, 0.59 or 0.96. And here we should know more about the flow regime. We should analyze this flow from another point of view in order to decide which one is correct, 0.59 or 0.96. Actually, in order to be able to answer for this question and to be able to decide which one is true, 0.59 or 0.96, we need to find critical depths at this canal. As I told, this one is not acceptable, but for the determination of the second determination of the true answer among between those two other routes, we need to find critical depths. Here you know that in this canal we have a rectangular cross section, and already we talked about calculation of critical depths in rectangular cross section. You might remember this formula. This is very useful and handy that we use in finding critical depths only in rectangular canals. You remember that Q is the unit discharge or discharge per unit width of the bottom, and we can find lowercase q by dividing the capital Q over bottom width, which equals to B. And for this example, B or bottom width is 5 meter. Therefore, unit discharge equals to 2 cubic meter per second per meter. And therefore, you can use this value to find critical depths. You square third root of the or cubic root of Q square over G. Q here should be 2 over 9.81 will give you the critical depths of flow in this canal equal to 0.74. So at upstream we see that flow depths, or which is if it is uniform, it is normal depths, or flow depths is above the critical depths. So what do you guess? Which kind of flow regime we had at upstream? If you guess that we have subcritical flow condition at upstream, you are correct, because when depth is higher than critical, therefore velocity is less than celerity, and we know that we can say that here fluid number is less than 1, therefore this is subcritical flow condition. And we see that when subcritical flow reaches to a hump, its elevation must be decreased, but its elevation cannot decrease in a way that it change flow regime from subcritical to supercritical. For example, if the elevation drops from here up to here, it must pass critical level, and it is impossible for this condition, and therefore the second elevation must be above the critical level. Critical level is 0.74. Among these two answers, only this one is higher than 0.74. Therefore, the answer would be 0.96. As you see here, y2 is 0.96, and therefore the correct answer for this problem, y2 equals to 0.96. Okay, so we can say that the critical depth is the limit for the flow over the hump. These depths will dictate the depth of flow above the hump. Uh, don't worry too much about this because when I talk about the graphical description of a specific energy, you will get the matter why critical depth is limit and why the drop cannot be in a way that it comes to the below of the critical energy. Okay, and now we can go to the second example in which height of the hump that creates critical flow uh, is analyzed. The question says that if the depth of a flow in a 2-meter wide rectangular channel is 2.5 meter, when the discharge is 4 cubic meter per second, estimate the height of the hump which would produce critical condition. Yes. The question says that we have a known depth at upstream, but the delta z can vary. We can increase hump or decrease it. But question said how much the maximum height of z for the case that this uh, drop or decreasing the water elevation creates critical depths at uh, above the hump. In fact, question says that we know y1, we know y2 equals to critical depths. Therefore, it is something like given, but indirectly, implicitly given. And in case that flow depth at here equals to yc, what would be the height of the hump at the second uh, section? And here you see that the discharge is also given equals to 4 cubic meter per second, and the channel bottom width equals to 2 meter. Okay, the question is the same with the previous one in terms of the ignoring the head loss, and therefore we can say that specific energy at section 1 equals to a specific energy at the second section plus the delta z. So we have y1, we know, like previous example, we know discharge, therefore we can calculate v1 in this way. Therefore velocity and flow depth is at hand at section 1. Therefore I have everything down for the specific energy at cross section 1. For the section 2, I know that the flow depth equals to critical depth. Therefore, Instead of y2 plus v square over 2g, I can write that yc plus vc square over 2g. What is yc? Critical depth, and vc is, you know that vc is the flow velocity at critical depth, which should be equal to the celerity, and it gives the condition of Froude number equals to 1. So I can easily find yc because this is rectangular cross section, and I know that yc equals to uh, cubic root of the, q, or you remember q is the unit discharge over g. Let's check it again. Then the discharge is 4 meter cubic. Okay, this is 4, therefore the bottom bit is 2. Therefore q, or a lowercase q, equals to 4 over 2. Yes, 4 over 2, and it should be equal to 2. Again, we in the formula we have q square over 2g. You remember this formula? Yes, q is square. Therefore, I divided 4 by 2 one times, I earned 2. Then I squared it. Therefore, this term should be again 4, and this is why you see here 4. And this equation gives me the critical depth equal to 0.4. I have critical depth, therefore I can either using celerity formula, which is celerity, yes, velocity equals to square root of g yc or gd, which for the case of uh, um, critical flow, d should be critical depth, or either using the well-known continuity equation, v equals to q over a. And I know that surface area, flow surface area, equals to yc times b, or the area of the rectangle at position 2. B is 2, yc from here is 0.74, and again vc, or critical velocity, would be 2.7. You can check at home also. This formula also must give us just 2.7 as a critical velocity here. So returning to the energy equation, I have yc and I have vc now. Therefore, the only unknown parameter is delta z, and replacing each or corresponding values from here to the energy equation, like here you see, I can calculate delta z, and delta z equals 1.42 meter. In fact, we can explain this problem in this way. If we have a discharge of 4 meter per second coming in this canal with the depth of 2.5 meter, if again we put a hump here with the height of 1.42, flow depth will decrease to be equal to 0.74 meter, which is exactly critical depth above the hump, or we will see critical flow in in section 2. And you remember that when I defined critical flow, I told that this is a unstable flow condition, and definitely after passing the hump, flow will try to change its regime to be either subcritical or supercritical. Okay, this is the third example in which water is flowing at a normal depth in a 3-meter wide rectangular channel with a bed slope of 1 to 500. If Manning's n equals to 0.025 and the discharge is 5 cubic meter per second, calculate the height of a hump which would produce the critical flow without causing breakwater upstream. Yes, if here the example is similar to the previous one, but the problem includes the Manning roughness. Therefore, to calculate discharge or velocity, if needed, you seems that you must use a Manning equation. And also the problem of choking or backwater is can be described like this. If you increase, you know that when we increase delta z for a certain height of dz, we will have a critical uh, depth here. And for the values more than the maximum dz, what will be happen? We will have a backwater, and it is some of the water comes back, and therefore we will see that elevation of water above the at upstream will increases. So if in a question calculate the height of a hump which would produce the critical, if in question the author either do not mention the appearance of critical flow, and if he says that maximum height in a way that we do not have backwater, or we are at the uh, at the level that with higher than this elevation for the obstacle, backwater will appear. It means that okay, assume the problem is in a way that y2 or flow depth at second position or at above the hump is just equal to the critical depth. This is the solution. I draw two different cross section at upstream and downstream. You know that bottom width at both equals to top width and equals to 3 meter. Discharge is given, but y1 is also unknown, and yes, y1 is unknown, and we know that at downstream or above the hump, this is the hump, we will have critical velocity. The bed slope equal S0 given 1 over 500 and equals to 0.002. And also Manning roughness equals to 0.025, and we are going to find delta Z. Again, in this example, loss of energy neglected. Therefore, what we have the energy equation like E1 equals E2 plus delta Z. And when we write each term based on the flow depth and velocity, and when we know that at second downstream or at second section elevation is yc, as I mentioned in previous example, instead of y2 and v2 we can use yc and vc. And let's see how many unknowns we have and how we can solve this problem. Okay, at first glance, y1 is unknown, v1 is unknown, yc is unknown, vc is unknown, delta z is unknown. It seems that everything is unknown. But we have a magic equation, as I told, yc critical depth in rectangular cross sections equals to third root of q squared over g. Now I calculate q because I have the capital Q. Therefore, discharge per unit width equals to 5 over 3 or 1.66667 cubic meter per second per meter or meter square per second. So YC is would be the third root of 1.66667 to the power of 2 over G, and the critical depth is at hand. Therefore, one of these unknowns is at hand. And as I told previously, when you have YC and you have discharge, you can clearly calculate velocity at this section. What is the velocity? Is the critical velocity, because this velocity is the velocity of a flow with critical depth. So velocity or celerity at this downstream or above the hump equals to 5 over 3 bottom width times YC 0.66, and velocity at this here would be 2.54. One noun, the other is noun, and let's continue to see how we can find the other unknowns, and our goal is to find delta Z ultimately. Okay, y1 is normal depth. Yes, y1 is normal depth, and we know discharge, we know Manning roughness, and therefore it seems that we must use Manning equation to calculate V1. But you know that when we are going to calculate velocity using Manning equation, you have to first determine the hydraulic radius. Hydraulic radius equals to the area over wetted perimeter. And here, this is a rectangular cross section. Area equals to 3y, wetted perimeter equals y plus 3, or 3 plus 2y. Therefore, area 3y over 3 plus 2y. This is hydraulic radius. You can replace hydraulic radius here, and S is given. So this is our Manning equation. And what we don't know, this is only the unknown. The only unknown is y1. And using some algebra, you can simplify this equation and solve in a way that you can find y1. As you see here, this is a kind of examples that we had in previous lectures, and we should use an iterative method in order to calculate y. And I started with y equals to 1, and then I calculated r hash, or this term, which is then I checked the assumption is equal to y1 or not. And finally, after several trials, I found that y1 equals to 1.2 gives me both sides equal, more or less equal. Therefore, y1 would be 1.2. If you know y1, again, q is at hand, you can calculate v1. Therefore, I did it, and we find v1 equals to 1.39. Now in this equation I have y1 and v1 and also I had these two terms, and now I can find delta z based on the corresponding values. And as you see here, y1 plus v1 square, v1 square over 2g equals to yc plus vc square over 2g plus delta z. And you can solve this problem for delta z, and you will see that the answer is 0.3 meter. Therefore, when the delta z is 0.3, we will have critical depth above the hump. Yes, these are three different kind of the problems that we can solve using energy equation. And this is all for today. In the next section, I will talk about the visualization of the specific energy, and in that lesson, we will see that why when water surface drops above the hum, it cannot pass YC, and it can be only reach to YC. Thank you for listening. Have a good day.